Hello, students, and welcome. Today, we are going to understand a very important topic in organic chemistry, one that you will definitely see in your exams, the structure of amines. And my goal is to make it very, very simple for you.
Right, let's start with a very simple question. You must have done this in your chemistry lab, no? You take a solution of ammonia or an amine, and it turns red litmus paper blue. We all know this shows it's basic. But why? This simple observation actually holds the key to the entire chemical personality of amines. Let's find out how.
So to really get why that litmus paper turns blue, we need to go back to the basics. First of all, what exactly is an amine? Okay, let's break this down.
At the most simple level, just think of an amine as a modified ammonia molecule. You can replace one or two or even all three hydrogens with some carbon groups. But, and this is the most important part, Beta, listen carefully, that lone pair of electrons on the nitrogen atom, it always remains. It is always there.
You see, this lone pair is the real hero of the story. It is not involved in bonding, so it is free. It is available. And this availability is the key to everything. It is why amines act as bases, and it is why they act as nucleophiles, meaning they are ready to go and attack positively charged centers. Always remember, everything comes back to this lone pair.
Now, I know what you might be thinking. Sir, this is all a little bit abstract. Electrons, lone pairs, and you are right. So, to make this idea much easier to remember, especially for your exam, let's use a very simple analogy. I'm sure you have seen a socket wrench from a toolkit. Just imagine that the main body of the wrench is our nitrogen atom. The different handles you can attach to it, well, those are like the hydrogen or carbon groups. They can be changed. But no matter which handle you put on, the wrench still works because of its turning action, correct? That turning action is exactly like the reactivity of our lone pair. Simple as that.
And this, my dear students, is why we teachers are always telling you that structure is so important. This whole concept exists to solve a fundamental problem, to explain why amines react the way they do. It connects what we can see in the lab, like the litmus test, to what is actually happening at the molecular level with atoms and electrons.
So, now for the important part. What is the picture that should come into your head the moment you hear the word amine? Let's build this mental image together, step by step, so that you will never forget it.
We'll do this in 4 simple steps. We will start with the nucleus, then the bonds. Then we will identify the reactive center, and finally, we will have our complete reactive pyramid.
Okay, step 1. Right in the middle, picture a central nitrogen atom. Now, I want you to think back to your chemical bonding chapter. Remember sp3 hybridization? That's what we have here. This nitrogen is sp3 hybridized, which simply means it's surrounded by 4 regions of electron density.
Step 2. Out of those 4 electron regions, 3 of them form bonds, and these bonds point downwards, just like the legs of a caver tripod. See? This is what gives us our basic shape, a trigonal pyramid.
Now, step 3 is the most interesting part. Wait a minute. sp3 means 4 electron domains, but we have only used 3 for the bonds. So where is the 4th one? Ah, that is our hero. It is not a bond. It is the lone pair of electrons sitting right at the top of the pyramid, pointing upwards like a small antenna. This is our reactive center.
And there you have it, step 4, the complete picture. A reactive pyramid with its electron-rich antenna at the top, just open and available in space, completely ready to react. This is what allows it to grab a proton and act as a base, or attack a positive center and act as a nucleophile. The shape is the reason for its function.
Okay, so we have the theory, we have the mental picture, but does this actually matter in the real world? Absolutely. Let's look at a very important application that you might be surprised by.
Think about something as important as clean drinking water. In many water treatment plants, they use special filters called anion exchange resins. And these resins are full of amine groups. That lone pair on the nitrogen, our little antenna, acts like a tiny magnet, attracting and trapping negatively charged pollutants from the water, making it pure.
So you see, this is not just some textbook theory. That pyramid shape we just visualized, with its exposed lone pair, directly explains how this vital technology works. It's a perfect, real-world example of how structure determines function. The availability of that lone pair is the entire key.
All right, so before we finish, let's quickly recap the 3 most important things you must remember for your exam. First, the core idea.
Please understand it. Don't just memorize it. The lone pair is the soul of amine chemistry. It is the reason for all its reactions.
Second, always keep that mental picture of the reactive pyramid with its antenna in your mind. And third, connect everything back to that simple, real-world example of the litmus test. If you can just remember these three things, the core idea, the mental picture, and the real example, I promise you this entire chapter will feel much, much lighter.
And now I will leave you with a final question to think about. We've established that the availability of that lone pair antenna is the key to everything, right? So what do you think would happen to its reactivity if we start attaching very large, bulky groups around that nitrogen atom? Would it still be as easy for it to react? Think about it. We will explore this in our next